Hey guys, welcome to week 3 here in section module 8.6. We're going to learn about difference of perfect squares. From what I recall, I don't really think you guys will struggle too much with this one. People tend to find it a little easier in some cases than what we did in 8.3 and 8.5. Those triangle mules can really get us. But you have to know your perfect squares in order to be pretty good at this. So let's practice that a little bit first. Perfect squares, what are they? A perfect square is an integer or value that is multiplied by itself. For example, 36 is a perfect square, but do you know why? Well, 36 is a perfect square simply because it has a number that's multiplied by itself to equal that. So, for example, in this case, the number is 6 because 6 times itself, again, so 6 times 6, is 36, which means 36 is a perfect square. So that's what the perfect squares are. They're a result of some number being multiplied by itself, right? 33, is 33 a perfect square? Well, is there a number that will multiply by itself to equal 33? And we really want integer. We want some kind of whole number. We don't really want a decimal or something of that sort. 33, I guess we'll find out. But spoiler alert, it is not a perfect square. Is 33 a perfect square? No. 33 can be factored into 3 times 11. However, that's not the same number multiplied by itself. It's not 3 times 3 or 11 times 11, right? It's two different numbers multiplied together, which we can do that any day of the week, right? We want specifically, though, we want to know, is there a number that multiplied by itself to equal 33? And the answer is no. There is no number because 3 times 11 makes 33, and there is no number like 5 times 5, 6 times 6, 7 times 7, nothing like that gets you 33. Is 4 a perfect square? Well, 4 is the result of 2 times itself, right? 2 times 2 equals 4. So therefore, 4 is a perfect square because I can find a number that multiplies by itself to equal 4. And that number in this case is 2. Exactly. Next, variables as squares. So variables as squares. Basically, if your variable has an even number exponent, doesn't matter if it's a perfect square even number or not. If it's a even number, it's a perfect square. So x to the 10th power is a perfect square. And it's because it's the result of x to the 5th power times itself. X to the 5th power times x to the 5th power makes x to the 10th power. Okay, so even numbers work that way. Odd numbers do not. Odd number exponents, I should say, right? Even number exponents and odd number exponents. So any even number exponent is a perfect square, like x to the 8th, or x to the 12th, or x to the 14th, or x to the 16th, right? Those are even number exponents. They are perfect squares, and the square root of them is just kind of half the exponent. We will talk plenty more about that. But if it's an odd number exponent, it will not be a perfect square. Yeah, here we go. We talked about it. X to the 5th times itself, x to the 5th, does equal x to the 10th. Okay, so, and that result is always going to be an even number exponent when you do that. X to the 9th. X to the 9th is not a perfect square, simply because it's an odd exponent value. And an odd exponent value, there will not be a perfect square for it. Okay, so just keep that in mind as we go. All right, second page. Factoring a squared minus b squared. So this is the main thing. I know it's kind of weird. We don't like to see letters a lot of times, but we'll make sure you understand this real quick. Is there a thing to click on here? Oh yes, there is. Okay, so it's a very simple puzzle, and we have so many examples here that will walk you through. But let me kind of take you on a journey real quick. Okay, kind of a journey to show you just kind of how easy these can be. So let's create a new whiteboard. Let's close that. Okay, close that again. All right, so this one, let me explain real quick what it's doing, right? A squared minus b squared equals a plus b parentheses a minus b. All right, this is kind of the rule of thumb of what happens, okay? So let me use an actual example, to really kind of explain what this means. So whatever the first part here is, should be a perfect square. So example, let's start with something basic like x squared. X squared is a perfect square, right? It's got the even number exponent, which is how you know it's a perfect square. And let's say minus 4, because we already did 4. We already know 4 is a perfect square, remember, because it was 2 times 2. So what you're going to do with your two terms here is you're going to take the square root of them, okay? The square root of x to the second is simply x, because it's just really x times x. And the square root of 4 is 2, because it's basically just 2 times 2, right? So you want to know what the perfect squares of them are. And then from that point on, if the square root of x squared is x and the square root of 4 is 2, then our answer will look like this: x plus 2, x minus 2. Just like this result here, a plus b, a minus b. So the a, in this case, the x, is the square root of that first part, and the b part, which in our case is 2, is just the square root of the second term. And it's always going to be 2 terms as well. You can't really do this method or this trick if there's like 3 terms or whatever. So it's really only going to be a difference of squares when you have 2 terms. Now, if you didn't yet realize this, here's the reason why it's called difference of squares. Difference means minus sign. So this is not going to work if there's a plus sign between them. If there's a plus sign between them, it is not factorable. You would consider it as prime, okay? Because it won't be factored. Okay, so it's very important that we see a minus sign between the 2 terms. So difference, right? Difference meaning a subtraction sign, of squares, meaning that the 2 things here that we are subtracting together have to be perfect squares. X squared, 4, we already know those are perfect squares because the square root of x squared was x, the square root of 4 was 2, right? And then you just simply apply this and you have your answer. There's no real fancy work involved. There's not like a long process or anything. It's just literally find the square root and then you write your answer. So let's try this with another one. Let's say I have x to the, let's say x squared again, right? Let's say minus 16, okay? So first and foremost, notice the minus sign, right? It's very important to pay attention to that because it's not factorable if it's a plus sign. So it has to be a minus sign for this to work, right? Now, notice both terms are squares, right? You have x squared, the square root of that is x, and the square root of 16 is 4, because 4 times 4 makes 16. So x squared was x times x, 16 was 4 times 4. So the square root is x and 4. So that's all the work I really had to do, was just find the square roots, because my answer now is simply going to be x plus 4 and x minus 4. One's going to have the plus sign, one's going to have the minus sign, so these do alternate, but it's simply just writing the 2 square roots come together, right? It also, you could write x minus 4, x plus 4. It doesn't matter the order which you write them, but one's going to be a plus and one's going to be minus. They're never going to both be minus. They're never going to both be plus. It's always going to be one is plus, one is minus. But they should be the same as far as x and 4, right? X plus 4, x minus 4. So if I did another one, let's say x squared minus 49. Again, I got the minus sign, so that checks out. And then we have the square root of this is x, the square root of this is 7, right? So my values are x and 7, meaning my answer would be x plus 7 and x minus 7. Simple as that, okay? So let's keep going here. Let's see if we can do some harder problems, all right? So they have their example 9x squared minus 16. So let's look at that. 9x squared minus 16. So again, notice the minus sign. Don't do anything if it's a plus. If it's a plus sign, you write prime or not factorable, okay? But it's minus, so we'll continue our work. So what's the square root of our first term, right? If you take the square root of 9x squared. Well, it is a perfect square. And think about it in parts. First, think about the square root of 9. Square root of 9 is 3, since 3 times 3 makes 9. And as we mentioned previously, the square root of x squared is just x, because it's x times x. So the square root of those together is 3x. The square root of 9 is a 3. The square root of x squared is the x. So this together makes 3x, right? And then the square root of 16. The square root of 16, as we just mentioned previously, is 4 because 4 times 4 makes 16. So square root of each term, right? You have to be able to do that. That's the only real math you need to do. Now we're ready to just go ahead and write our answer. We've got our two terms. One's going to be plus, one's going to be minus, and we are good to go. 3x plus 4, 3x minus 4. That's our final answer. We're done. We're ready to move on. Okay? So let's check that work real quick. Check your answer, right? So there are only two terms. Yes, they're both perfect squares. Yes, there's a subtraction sign, as we mentioned. Does it actually work out the whole problem? I'm not sure. Well, here's an example of the perfect squares that I was showing you. They've got x squared minus 4. So the square root of both of those would be x and 2, which is why you see x plus 2x minus 2 as its answer. The second one, you see x squared minus 36. Again, we know that x squared is x, and 36 is 6 when you take the square root of them. So you have x and 6, which means your answer would be x plus 6 and x minus 6. And then the last one, x squared minus 9, right? We did that. So the square root of x squared is x. The square root of 9 is 3. So you have x and 3. So your answer would be x plus 3, x minus 3, right? So about the binomials, one's always going to be a plus, one's going to be a minus, right? One's positive, one's negative. There's always x plus 3 and then x minus 3, or x plus 4 and then x minus 4, right? Again, they're not going to ever be both plus or both minus. It's going to be one's positive, one will be a negative. All right? It is the same term and the square root of the first term of the original binomial. Sure. Okay, it is the same term and the square root of the second term of the original binomial. Exactly. So it's just the square roots and the plus and minus. So there's a video on 9x squared minus 4. If my video is not doing very good, then you can check that one out. You can do the try it problem, but let's move on to page 3. All right, now getting a little fancier here, okay? So let's look at the example they're giving out here. 3x squared minus 27. 3x squared minus 27. Now, first thing we're going to notice the minus sign. Perfect, okay? Because if there's a plus sign, we don't even want to do the problem, right? Don't waste your time. But it is a minus sign, so we're good. Now, here's the problem, though. 3 is not a perfect square. There's no number that multiplies by itself to equal 3. 1 times 1 would be 1. 2 times 2 would be 4. 3 times 3 would be 9, right? 1, 4, 9. 3 is not a perfect square. Okay, 27 is not on that list either because there's no number. The square root of 27 would be a decimal. There's no number that multiplies by itself to make 27. Now, let's go ahead real quick and let's write out a list of perfect squares. Let's say if I took 1 and I multiplied it by itself, I'd get 1, right? So 1 is a perfect square. If I took 2 and multiplied it by itself, I would get 4. 2 times 2 makes 4. So 4 is a perfect square, right? If I took 3 and multiplied it by itself, I'd get 9. 9 is a perfect square. So notice 2 is not a perfect square, 3 is not a perfect square, 5, 6, 7, 8 are not, right? It's only these specific numbers. If I took 4 squared, I'd get 16, which means that 10 would not be a perfect square. 11 will not be a perfect square. All the numbers between 9 and 16 won't be perfect, but 9 and 16 are, right? So 5 squared. 5 squared would be 25, so 25 is a perfect square. 6 squared is 36, so 36 is a perfect square. Right, you get the idea. 7 squared is 49. 49 is a perfect square. 8 squared is 64. 64 is a perfect square. Right? 9 squared is 81. 81 is perfect. So these are the numbers we're looking for. These are the perfect squares. 3 is clearly not a part of that list. 27 is clearly not part of that list. So what do we do? Right? Can I factor this? I can't do difference of squares, right? Because I don't have a difference of squares. However, we do know, what we've done in the past, is a GCF. Notice the first thing you should actually see here is the fact that there is a GCF, something you can factor out, right? Going back to the GCF method. Both terms here are divisible by 3, which means we can factor the GCF of 3 out, leaving x squared minus 9 in its place. And now, with the 3 factored out, this is now a difference of squares problem because both terms are squares, which means I can continue factoring the rest of this into Well, the square root of x squared is x, and the square root of 9 is 3. So that would factor into x plus 3x minus 3. But of course, don't forget the GCF is still going to be lingering on the outside there. So this would be your final answer for a problem like that. So sometimes they try to trick you. They give you a question that does not have perfect squares in it, but you need to remember to check to see a GCF first. Is there a GCF that you should try to take out first? And sometimes there is. And then in that case, even after you've done GCF, we are not done factoring, because now after the 3 came out, we had x squared minus 9, which you need to recognize as, hey, I can still factor that by difference of squares because I've got the minus sign, and x squared and 9 are both perfect squares. So remember, you would have to keep an eye out for that to factor even more. All right. Yes, this is showing you all the steps. It gives you the answers. We're good on all of that. Let's try page 4. Okay, factoring numerical expressions. It's kind of weird, in my opinion, because we have these numbers, but the rule still applies the same way. Okay, so let's look at, they've got this 28 squared minus 22 squared thing. Let me kind of write that down. 28 squared minus 22 squared. Now, in this case, it's actually really a little easier. The whole purpose of this is to try and do it without a calculator, because obviously anybody could just type this in a calculator and get the answer. But the idea is, okay, 28 squared is simply 28 times 28. So its square root is just a regular 28, not the 28 squared, but the regular 28. The square root of 22 squared would just be the regular 22. So you're just looking at the regular number there, not the squared version of it. Okay, so these are the two numbers that you'd put together. You'd have 28 plus 22 as one, and then 28 minus 22 as the other, because remember, 1 plus 1 minus. And then you would just kind of, simplify some of this. Let's see, what is this? This adds up to 50. 28 plus 22 is 50. And then 28 minus 22 is 6. So you have, this becomes 50. This becomes 6. So 50 times 6, and then you get your answer that way. For some of us, 50 times 6 is easier to do in our heads than 28 squared minus 22 squared. So that's why they come up with this little trick for you to be able to find the answer. Both of these would equal 300, but this is kind of a method of breaking it down so you can kind of do it in your head more than, relying on a calculator. So let's see if there's another example. It's got the 53 squared minus 47 squared. So 53 squared minus 47 squared. Again, the squared already there means that the square root of it will just be the basic number, 53 and 47, right? Just without the squareds. So with those two numbers, you would have 53 plus 47 as one group, 53 minus 47 as the other group. Remember, because you just take the two values, 1 plus 1 minus, and you're good. So now you try to do this in your head, right? 53 plus 47 is 100, and 53 minus 47 is 6. So now I know I multiply these together. 100 times 6 means the answer is 600. So this whole thing equals 600. It's just, this you can't really work out in your head, but when you break it down, you can actually kind of work it out in your head and get the answer of 600 without needing to use a calculator. Okay. So of course the next one will be 15 plus 10, 15 minus 10, as you can see, which means it'd be 25 times 5. And you can calculate that again without a calculator, which is nice. Okay, so now let's look at this example. You can obviously see it's already fully worked out, but let me try to break it down for you step by step. So they have x squared plus 2, or x to the third plus 2x squared. So x to the third plus 2x squared minus 9x minus 18. Minus 9x minus 18. This looks familiar. We have 4 terms, and when you see 4 terms, I think the first thing you should try to think of is grouping. But before we do that, let's just check to see if there's a GCF overall. Do all 4 terms have a GCF overall that we can factor out? The answer there is no. So yeah, we will resort to factor by grouping. So to group them, we will group the first 2 terms together and the last 2 terms together. Now the GCF of the first group, both of them have at least an x squared in them, so we're going to factor that x squared out. And then what we have left would be a single x plus 2. So if you are not sure how to factor by grouping, you're a little bit behind. You need to go back and watch, I think, is it section 8.2, I think is what it is. 8.2, you need to go back, rewatch that. Maybe even 8.1, to get factor by grouping. The second group, it's factor. They both can be divided by 9. And since this first term is negative, we'll factor out a negative 9. So we'll bring that out, which leaves us, let's put that back in parentheses, which leaves us with regular x plus 2 again. So as we're expecting to see, we have the common binomial factors. So that means my answer, the inside part is x plus 2, and the outside part is x squared minus 9. Now, a lot of people would stop there going, hey, look, I factored by grouping. We're all done, right? The answer is, are we though? Which is, the answer is no. Because if you look at your answer, x plus 2 cannot be factored anymore. However, x squared minus 9 can be. You have to recognize, hey, look, that's a difference of squares. I can actually go ahead and factor that even more. So yes, sometimes you have to be aware that, hey, you can't just assume the problem's done. You get to a certain point, go, hey, look, I've done all my factoring of that method, so that must be it. And the answer is not always. Check the result to make sure nothing else is factorable. This case, that we do see x squared minus 9, and we can see that we would still have to factor it. So we know the square root of x squared is x. We know the square root of 9 is 3, so that's going to turn into x plus 3, x minus 3. Of course, don't forget, though, the x plus 2 factor still exists. It didn't just disappear. It's still just chilling here. But we had the x squared minus 9 part factored into x plus 3, x minus 3. And so now everything is fully factored. This would be your final answer because you can't factor any of those pieces any further. And I think that's what they show you on here. Yes, they show you that as well. So be aware of that. Let's try example 2 while we're here. So 6x to the 4th plus 4x to the 3rd. Let's see here. 6x to the 4th plus 4x to the 3rd. Minus 6x squared minus 4x. All right, now, there we go. All right. So first thing, there is definitely a GCF here between all 4 terms. So before I factor by grouping, let's pay attention to the fact that every term can be divided by a 2, and every term has an x in it as well, meaning I can factor an x out with it. So let's factor that entire thing out. Let's take the 2x all the way out here. And let's see what else we end up with. So 6 divided by 2 would turn into 3. This would be x to the 3rd. 4 divided by 2 would be 2. This would be x to the 2nd. This would be minus 3x. And then x cancels there, so it would be minus 2. So factor the GCF out. And now I still have 4 terms. So I can factor by grouping now. So I'm going to group the first 2 terms together, the last 2 terms together. Now remember, the 2x is chilling here. It's not really relevant for the rest of our factoring, but it is still a part of our answer. So let's not forget that in our final answer at the end, we should have that 2x in front. But let's focus on our grouping. So our grouping, we can take out of the first group an x squared, GCF of x squared, so we'll take the x squared out. And that leaves inside, it would be 3x plus 2. And for the second group, both terms are negative, so we're going to factor out a negative 1. And then inside, we're going to be left with a positive 3x plus 2 again. So 3x plus 2. So we have the common factor, the inside part of 3x plus 2. And we have the outside part as well, x squared minus 1. X squared minus 1. And just for fun, don't forget the 2x as well. Just It's still just chilling there, okay? So a lot of you would stop here and go, hey, look, I've done the GCF. I've done all the factor by grouping. There can't be any more. But the answer here is there is still more, because something here is still factorable. And it's the thing in blue. X squared minus 1 is still factorable. It's still factorable by difference of squares again. So difference of squares. Okay? So the square root of x squared is x. The square root of 1 is still 1, because if you remember, where did I do that? Write those numbers down earlier. Here they are. Right? 1 is still a perfect square, because 1 times itself is equal to 1. So that's why, this is still factorable with that 1 there. So that means if you pair these together, this becomes x plus 1, x minus 1. 1 is plus, 1 is minus. So don't forget, the 3x plus 2 could not be factored anymore, but it still exists. It's still here. And the 2x on the outside could not be factored anymore, but it's still there as well. So now this is your final answer, since everything is fully factored. There's nothing left that can be factored. So this problem is a good problem because it pretty much uses almost everything we've learned over the past 3 weeks. We've used GCF, right? We used grouping, and we even used difference of squares. So 3 methods of factoring all in one problem. So it's a lot, but I think we already know GCF and grouping pretty well because we've already done that in previous weeks. Difference of squares is the only new thing about this problem, but it's not a very difficult one in my opinion, because you just take the square roots and you just pair them together as a plus and a minus, x plus 1, x minus 1. It's not very exhaustive, okay, in my opinion. You might think differently. So don't forget to check out example 3. It's very much the same. There is no GCF overall, but you factor by grouping, and then you would do your difference of squares again. So let's see if there's any more tricky questions to do. Nope, these are just going to be some practice problems for you. I suggest you seriously work through a lot of these. I'm guessing page 6 is going to be even more, right? Yeah, it's an activity as well. Please work through those before you take the quiz. If you have questions on them, please ask those questions in the discussions tab here on the left, if any of these don't make sense to you. But if you do get them and you're doing all right, go ahead and start the quiz. And we will see you guys in the next section, 8.7. All right? Adios.